Yeah, good afternoon, guys. We are meeting once again. Power machines, N5. Our topic, gas processes. The question that we are dealing with today, it reads, a gas at 22 degrees Celsius is compressed isothermally from a pressure of 120 kilopascal and a volume of 4.2 cubic meters. The volume ratio of the original volume to the final volume is 3:1, and then gas constant is given as 0.88, and then our CV is given as 0.712. So the most important thing, we can write our data. Anyway, at this point, I think it's going to be clear. So our data, we have our T1, which is 22 degrees Celsius. Don't forget, we need to change it to Kelvin. So we add plus 273. So 22 plus 273, it gives us 295 Kelvin. We are also given our P1, which is 120 kilopascal. And then our V1 is given as 4.2 cubic meters. We are also given our compression ratio. Our compression ratio is given as 3:1. And then we are also given our gas constant, which is given as 0.288 kilojoules per kg Kelvin. We are also given our CV, which is 0.718 kilojoules per kg Kelvin. Now, the most important thing here, the topic that we are dealing with, it's an isothermal process. So you must remember isothermal process, or when they say a gas is expanded or it is under isothermal conditions, you must remember that T1 is equal to T2. So T1 is equal to T2, which is to say when the temperature was 22 degrees Celsius, our T2 was also 22 degrees Celsius. When our temperature is 295 Kelvin, T1 and T2, they are the same. So question number 1, the question says, calculate the final volume. The simplest way when you are doing the question like this, already you are given what you call a compression ratio. When they said the volume ratio of original to final is 3:1, that is what you call a compression ratio. Therefore, we will not waste much of our time. To get our V2, we just apply that compression ratio. Now, it becomes 1/3 times our original volume. That's what they said on the expression. The volume compression ratio of original to final is 3:1. So it becomes 1/3 times our V1 is given as 4.2. So if we say a third of 4.2, it gives us 1.4 cubic meters. That becomes our V2. That becomes our V2. Now, on question 2.2, they want the mass of the gas. So we can use our formula PV equals to MRT. Perfect. So it becomes P1, V1, MRT1. And then our P1 is given as 120. Our V1 is given as 4.2. Our mass, that's what we are looking for. Our gas constant, 0.288. T1 is 295. So let's substitute. Let's get our mass. If we do our calculations right, we are getting 120 times 4.2 divided by 0.288 times 295. We are getting something like 5.932. 5.932 kilograms. And then on 2.3, we are supposed to calculate the final pressure. They want us to calculate our P2. So there are many formulas which we can use, but under examination conditions, just try to stick to simple formulas. Remember, this is an isothermal process, which in many cases, our cardinals, our temperature cardinals and our volume conditions, they exceed up to cardinal point number 4. So which is to say, if this we have P1 V1 equals to MRT1, we can also increase it to P2 V2 equals to MRT2. We can increase it to P3 V3 equals to MRT3, P4 V4 equals to MRT4. But in this case, we are just ending at this point. So we can use our formula P2 V2 equals to MRT2. Do we have our P2? No, we are looking for P2. And then our V2, yes, we just calculated now, it's 1.4. Our mass, 5.932 times our gas constant was given 0.288. And then don't forget, this is an isothermal process, and we said isothermal process, our temperatures are equal. So our T1 is equal to our T2, which is 295. So from there, let's make our P2 subject of the formula. So we have 5.932 times 0.288 times 295 divided by 1.4. Divide by 1.4. We are getting something like 359.988 Kelvin, rather kilopascal, which is in essence is 365 kilopascal. That's our final pressure. And then on question number 2.4, they want us to calculate our work done. So this is a isothermal process. We have about 2, if not 3, formulas which you can use to calculate our work done. We can use the ratio of our temperatures or the ratio of our volumes as well as our temperatures. Is 2 gives us one and the same thing. So we can start off on 2.4. Please allow me to write it here. We can say, therefore, work done equals to P1 V1 ln of V2 over V1. These formulas are there on a formula sheet, so there's no need for you to cram them or to stress about them. So if you are to use this one, we have our P1, which we said it's 120. Our V1 is 4.2. Ln of our V2, which we got as 1.4 divided by our V1, which is 4.2. So let's substitute 120 times 4.2 times or ln of 1.4 divided by 4.2. Let's see what are we getting as our volume. I'm getting a minus 553 minus 553.7 kilojoules. We are getting other ways. There's loss of energy in the system, which shows that our answer is right. Now, in the exam, if you are also fast, because this formula for work done is given on a formula sheet, and the second one is also given, we can use it as an alternative method to see whether our answer is right or is not right. From the same formula for Boyle's law or Charles' law, P1 V1 equals to MRT1. So we say P1 V1 equals to MRT1. So we can use here our MRT1 ln of we use the ratio of our pressures, it becomes P1 over our P2. So this formula is also there on your formula sheet. So let's substitute our mass 5.932, our gas constant 0.288, T1 295, lean off our P2. We got 360. Our P1, it was given it's 120. So let's substitute and see what are we getting there. Let's see, we have 5.932 times 0.288 times 295, lean 360 over 120. Let's see what are we getting there. I'm getting negative 53.682 kilojoules. So this is what I'm getting. Yeah, but there is a small error that I think we made on our formula here. When you're using, can you check on your formula? Work done equals to MRT1, lean off, rather it has to be P2 over P1. Yes, it has to be P2 over P1. So in other words, you just do the opposite so that our answer remains with the same sign. If you do the inverse, it will give you a positive sign. So we need to be consistent. We need to get our negative answer on that point. Let's go to 2.5. We need to calculate our change in internal energy, delta U equals to MCV into T2 minus our T1. We are just substituting because already we have everything at our disposal. So we have our mass 5.932, our CV, which is 0.712, our T2, we say it is 295 minus 295. Remember, it's an isothermal process. And if you see on the question, they are saying our main max is 2 max. We are just calculating because the marks are given as 2 max, but in essence, this one was supposed to be 1 because we are calculating nothing. Because you must always remember change in internal energy, if it's an isothermal process, it is always equal to 0. The reason being the temperatures are constant. So we don't need to punch this. Our answer becomes 0 kilojoules. So we just have to calculate because of, we see the mark allocation is 2 max. Maybe they just want to see you showing some steps, but still it will give us a 0. Let's go to 2.6. They want us to calculate amount of energy. So they want heat absorbed or heat exerted. So in an isothermal process, we don't waste our time. Once again, calculating the heat lost or heat gained. We simply say, remember, work done during isothermal process equals to our Q. Therefore, Q equals to minus 553.7 kilojoules. It shares the same units, so it shows that indeed this energy was what lost. It was not what gained, because our sign here, it gave us a negative sign. And then lastly, 2.7, they want us to calculate our delta S, our change in entropy. So change in entropy, delta S, this formula is once again there on your formula sheet. Delta S equals to M bracket R ln of V2 over our V1. That's where our formula ends. We don't need to go far here because remember, so you can add plus 0, because if we use the ratios of our temperatures, they will just give us a 0 because our T1 and our T2 are equal. So let's substitute our mass is 5.932 times 0.288 ln of our V2, which is 1.4, our V1 4.2. So if we substitute here, we are supposed to get something like, let me punch, 5.932 times 0.288 ln 1.4 over 4.2. So I'm getting something like negative 1.88 kilojoules. So kilojoules rather per Kelvin. Don't forget, that's our change E of entropy. So basically, that's how we are supposed to tackle a problem like this. It's a very simple question, but you must understand first the process. Now, as we are wrapping up, let me try to use this slide also to summarize the last process of isochoric process. Now, an isochoric process, it is a process which is conducted in such a manner that our volumes are equal. In other words, V1 equals to our V2. The second thing that which we need on an isochoric process, remember the formulas that we have are we have work done equals to 0 because we are supposed to use on our formula of work done, which is similar to the one for isobaric process, because our formula includes our V1 and our V2. Therefore, our answer to give us a 0. So work done during isochoric process equals to 0. And then our Q during isochoric process equals to mCV into T2 minus our T1. It's just the opposite of isobaric. Remember, isobaric Q equals to mCP into T2 minus our T1. So NH isobaric process, we use a CP here, constant pressure, but NH constant volume, we use our CV, which is also our specific heat capacity at constant volume. And lastly, our delta U, which is our change in internal energy, delta U equals to mCV into T2 minus our T1. Now, the other formulas of P1, V1 equals to mRT1, we can use it anyway, regardless of the process. Thank you so much. Meet you next time. Bye-bye.